Welcome. So let's start by looking at a completely broken equation that you probably live with every single day.
Yeah, we all do, honestly.
Right, because usually when we think about getting what we want out of life, there is this underlying assumption of a really simple linear transaction. Like you have a craving, you satisfy that craving, and then you experience fulfillment.
It feels like a fundamental law of physics, doesn't it? I mean,
Mm.
thirst, water, relief,
Mm.
hunger, food, satisfaction.
Exactly. But wait, actually, no, that's the whole problem. It used to be like that. But look at your modern landscape. I mean, look at your phone right now. You have unparalleled access to absolutely everything.
Right, infinite entertainment, instant food delivery.
Endless social validation at the tab of a glass screen. You possess all the water in the world, and yet there's this pervasive, lingering sense of total emptiness.
It's basically a psychological mirage. You know, you see the water, you run toward it, but the moment you scoop it into your hands, it turns to sand.
Wow.
You're left standing there parched, scrolling to the next video, opening the fridge for the 5th time, and you're completely unsatisfied. And what we are doing today in this deep dive is taking apart the actual biological blueprints of that exact mirage.
Because we are going to answer the core paradoxical question of your modern life, which is, why do you feel more empty the more you consume?
Right.
And the answer, incredibly, lies in a massive stack of neurobiological research sitting right here on the desk between us. We are looking at the dopamine system today. We are completely tearing down the pop culture myth that dopamine is your brain's magical pleasure chemical.
Which is going to require us to look really closely at the architecture of your own mind. And if you look around this space we've set up, this dimly lit library, the illuminated anatomical models of the brainstem glowing on the oak desk.
It looks amazing, by the way.
Thanks, yeah. And, you know, the intricate hexagonal chemical structure slowly rotating on the monitors behind me, you are seeing the biological reality of your behavior right here. We are living through a neurological famine.
A neurological famine.
Yeah. Your brain is being overfed on cheap dopamine, but it is fundamentally starving for genuine purpose.
Well, let's start with that pleasure myth, because I think if you stop anyone on the street, they will tell you dopamine equals happiness. I know I used to think that, absolutely.
Most people do, yeah.
Right, like I ate a phenomenal piece of chocolate cake, I feel an immense rush of pleasure. Are you telling me that feeling, that actual sensation of enjoyment, has zero to do with dopamine?
I mean, zero might sound extreme, but functionally, yes.
Wait, really?
Yeah. The sensation of pleasure, what neuroscientists call hedonic liking, is mediated by entirely different systems in your brain, primarily the opioid and endocannabinoid systems. Dopamine is not the pleasure itself.
Okay, then what is it?
Dopamine is the motivational salience.
Yeah.
It is the wanting.
I'm struggling to separate those two things because wanting and liking feel like the exact same sensation when I'm like staring at a dessert menu.
They feel interwoven because in a healthy environment, they evolve to fire sequentially. First you want, then you like.
Yeah.
But the research pulls them apart completely. Look at the animal models detailed in these papers we have. Researchers can take a rat and genetically or chemically engineer its brain to have absolutely zero dopamine in its reward pathways.
Okay. And what happens to the rat? Does it just sit there looking depressed?
Worse, actually. It does nothing. It loses all motivation.
Right.
If you put a bowl of its favorite sweet food on the other side of the cage, the rat won't even walk over to it.
Wow.
It will literally sit in the corner and starve to death. The drive to act is just completely gone.
I assume because the pleasure chemical is gone, so it thinks the food will taste like cardboard?
No. And this is the vital distinction right here. If you take that exact same dopamine-depleted, starving rat, and you physically pick up a dropper and place the sweet sugar water directly onto its tongue,
Yeah.
the rat's face will light up. It displays all the classic, measurable facial expressions of intense pleasure. It licks its lips. It shows rhythmic tongue protrusions. It still possesses the full, unadulterated capacity to enjoy the food.
Wait, are you serious? So it loves the food, it just completely lacks the motivation to pursue it.
Exactly.
Yeah.
So dopamine isn't the fireworks display.
It's the match.
Yes. It's the motivation to walk outside in the cold to strike the match. It's the chemical of desire, of anticipation, of calculating that something out there in the environment is worth expending your precious biological energy to go get.
Okay, let's unpack this, because mechanically, where is this even happening? When I picture dopamine, I just picture my entire brain kind of marinating in it like a sponge.
That's a common misconception.
Right.
It's actually highly localized. Out of the roughly 86 billion neurons in the human brain, There are only about 400,000 dopaminergic neurons.
400,000, that's nothing.
It's incredibly rare. They make up a tiny fraction of a percent of your brain, but they cast a massive dictatorial net over your behavior.
I was actually reading the methodology in the notes about how we even know this.
Yeah.
In 1964, these two researchers, Annika Dahlstrom and Kay Folks, mapped these specific cells. But how do you find 400,000 specific cells in a sea of 86 billion?
They used a technique called the Falk-Hillarp fluorescence method. They took slices of brain tissue, freeze-dried them, and then exposed them to formaldehyde gas.
Okay.
When they put this tissue under an ultraviolet microscope, the different neurotransmitters literally glowed in different colors. The neurons containing catecholamines, like dopamine, fluoresce this brilliant, bright green.
Is so cool.
Yeah, it's beautiful. They mapped these growing clusters and labeled them starting with the letter A for aminergic.
And the clusters we care about today are A8 through A14, right? Specifically A9 and A10.
Yes, exactly. A9 is a cluster located deep in the brainstem called the substantia nigra pars compacta. And substantia nigra translates from Latin as black substance.
Wait, why black? I thought you just said it glowed green under the UV light.
Well, under UV it fluoresces green, sure. But to the naked eye, like in an unstained slice of human brain, this cluster of cells actually looks like a dark, swooping streak of charcoal.
Oh, interesting.
Yeah, that dark coloring comes from a pigment called neuromelanin, which is just a byproduct of dopamine synthesis. This dark streak projects its axons up into the striatum. We call this the nigrostriatal pathway.
And what does that pathway do?
Its fundamental job is the facilitation of voluntary movement.
Movement. Wait, so we aren't just talking about this psychological desire to get the cake. We are talking about the literal mechanical initiation of putting one foot in front of the other.
Exactly. Dopamine sets the threshold for initiating actions. It dictates how much internal friction you have to overcome to evoke a physical behavior.
Yeah.
If you have high dopamine activity in this pathway, that threshold is lowered.
For you just go.
Right. You are highly motivated, you move quickly, you might even become impulsive, showing psychomotor agitation. You just move.
And if the threshold is high, like if you don't have enough dopamine.
If the threshold is high, you see the tragedy of Parkinson's disease. In Parkinson's, the dopamine-producing neurons in that dark streak, the substantia nigra, are progressively dying.
Oh, wow.
As the dopamine drops, the threshold for action becomes impossibly high. The result is stiffness, bradykinesia, which just means slowness of movement, and a profound, agonizing difficulty in simply initiating a step forward.
That's heartbreaking. So the brain's motor cortex might be screaming walk, but the transmission has no fluid. The physical drive is just gone.
Precisely. That makes the separation between wanting and liking so intensely physical.
Okay, so A9 is the movement. What about the other glowing cluster, A10?
A10 is the ventral tegmental area, or the VTA.
Sure.
This is the origin of the mesolimbic pathway, which projects forward into a region called the nucleus accumbens. And it's also the origin of the mesocortical pathway, which projects all the way up to your prefrontal cortex.
And what does this one do?
This A10 cluster is the circuitry of reward, addiction, emotion, and complex cognition.
Aha. So this is the circuitry that modern technology has completely weaponized against us.
Without a doubt.
The sources highlight this landmark 1998 study published in the journal Nature. Researchers put humans in PET scanners, which track radioactive tracers binding to receptors in the brain, and they had them play a video game.
Right, and it was a very rudimentary video game by today's standards. It was a tank simulation.
Yeah, you're just navigating a virtual tank through a battlefield, picking up virtual items. The game provides 0 actual calories. It provides 0 shelter, 0 evolutionary survival benefits. Yet the PET scans showed massive dopamine release in the striatum.
It's incredible.
The game hijacked the ancient survival circuitry by creating a perfectly calibrated, constant state of wanting.
Think about the implications of that for your daily life. The platforms you use, the infinite scrolling feeds, the match 3 games on your phone.
Oh, I play so many of those.
Right. But they are not designed to give you a satisfying conclusion. If they gave you a conclusion, you would put the phone down.
You'd feel done.
Exactly. They're meticulously designed to keep you in a perpetual state of anticipation. They constantly pluck that dopaminergic string, creating a feeling of urgency and desire, but purposefully withholding the actual hedonic fulfillment.
So I have this underlying question bubbling up. We've established that dopamine is this engine of wanting. But how can one single tiny molecule do all these vastly different things?
How do you mean?
Like, how does the exact same chemical make one person initiate a physical step forward and make another person compulsively scroll through short-form videos until 3 a.m. and make a third person crave cocaine? It's just a molecule. It doesn't have a brain of its own.
That is a great point, and it brings us to the molecular machinery. The dopamine molecule itself is just a key. The effect it has is entirely dependent on the locks.
The locks being the receptors.
Yes, the dopamine receptors on the receiving neurons. Your body has 5 distinct types of dopamine receptors, labeled D1 through D5. They all belong to a massive superfamily of proteins known as G-protein-coupled receptors, or GPCRs.
I remember the GPCRs from the provided materials. The diagrams of these things are wild. They look like a snake weaving in and out of the cell membrane.
That's actually a highly accurate way to visualize it. They are known as 7-pass transmembrane proteins. The protein chain literally threads itself back and forth across the cell's outer wall 7 times.
Wow.
And the head of the snake sits on the outside of the cell in the synapse, waiting for dopamine. The tail of the snake hangs down inside the cell.
Wait, so the dopamine never actually enters the receiving cell?
No, it never enters, it just docks.
Like a key in a lock.
Exactly like that. When dopamine binds to the head on the outside, the entire snake contorts. It physically changes its 3-dimensional shape. That contortion causes the tail inside the cell to wiggle, which kicks off a massive cascade of chemical reactions.
Okay, so the locks change shape.
Right, and we divide these 5 receptors into 2 distinct families based on what that tail does when it wiggles. The D1-like family, which includes D1 and B5, and the D2-like family, which includes D2, D3, and D4.
Let me guess, they do completely opposite things.
They do. The D1-like receptors are stimulatory. When dopamine contorts them, their internal tail grabs onto a protein called G-alphas. This G protein acts like a switch that turns on a cellular factory called adenylate cyclase.
And what is the factory building?
It turns out a messenger molecule called CAN-AMP. You can think of CAN-AMP as an internal alarm bell.
Okay, alarm bells ringing.
Right.
Yeah.
When CAMP levels rise, it activates kinases, which are proteins that run around phosphorylating or basically energizing other proteins.
Okay.
This ramps up the cell's overall electrical activity. It promotes memory formation, sharpens attention, and facilitates locomotion. It basically steps on the gas.
So the D2-like receptors must be the brakes.
Precisely. The D2-like receptors couple to a different protein, G-alpha I. The I stands for inhibitory. When activated, this protein physically travels over to that adenylate cyclase factory and shuts the doors.
It turns the factory off.
It halts the production of CAN-AMP. The alarm bells go quiet, the kinases power down, and the cell's activity is dampened.
Okay, I'm slightly lost on the behavioral output of that. Because if the D2 receptor shuts down the cell's activity, how does that translate into making me do something?
What do you mean?
Like, if I want a piece of cake, shouldn't my brain be fully energized and active? Why would I want a receptor that hits the brakes when I'm trying to be motivated?
It's a brilliant question. You have to think of the brain as a notoriously noisy place. There are millions of signals firing all the time, suggesting a million different actions.
Eat the cake, check your email, scratch your nose.
Worry about your mortgage, exactly.
Yeah.
If you want to successfully execute one action, you don't just need the gas pedal to drive toward the cake. You need the brakes to suppress all the competing noise. The D2 receptor quiets the irrelevant pathways, so the primary goal can actually be achieved.
Okay, that makes perfect sense. It's like turning down the radio so you can read a map.
Exactly. But the sources also mention that dopamine has a whole other set of tools that don't even use this G protein factory system.
Oh, really?
Yeah, this is a relatively recent fascinating discovery. It's called G protein independent signaling. Sometimes, when a D2 receptor is activated, instead of messing with the CAMP factory, its tail recruits a large scaffolding protein called beta-arrestin 2.
A scaffold, like construction scaffolding.
Exactly like that.
Yeah.
It physically holds different proteins together so they can interact. This beta-arrestin 2 scaffold grabs onto enzymes inside the cell with names like ACT, PP2A, and GSK3.
That's a lot of acronyms.
It is, but the important part is that by forcing these specific enzymes into close proximity, it bypasses the normal alarm bells and modulates entirely different aspects of your behavior, specifically how you respond to psychostimulants and how your brain encodes addiction.
Which brings us to the dark side of this machinery. How do drugs of abuse, or even just our daily modern behavioral vices, hack into this delicate system of gas pedals and scaffolds?
Let's use cocaine as the starkest example here.
Yeah.
Under normal, healthy circumstances, your A10 neurons release a burst of dopamine into the synapse the gap between the cells.
Right.
The dopamine hits the D1 and D2 receptors, delivers the message of wanting, and then it needs to be cleared out so the system can reset. The cell that released it has a vacuum cleaner on its surface called the dopamine transporter, or DAT.
Oh, so it sucks the dopamine back up to be recycled?
It cleans up the synapse. But cocaine physically clogs that vacuum. It binds to the DAT and just jams it.
Uh-oh.
Suddenly, the dopamine cannot be cleared away. It just pools in the synapse, building up to massive unnatural levels, repeatedly and violently slamming into the D1 and D2 receptors.
Wow.
This creates an overwhelming, deafening signal of incentive salience. It tells the brain, this is the most important thing for our survival in the history of the universe.
But the brain doesn't just sit there and take that abuse, right? The research you provided dives deep into neuroplasticity. The brain pushes back.
It has to, or it would fry. When you expose this delicate receptor system repeatedly to unnatural superstimuli, whether that's a flood of cocaine or highly engineered hyperpalatable junk food, or even the endless algorithmic novelty of a social media feed.
Yeah, the doom scrolling.
Exactly. The receiving cells physically alter their own structure to try and turn down the volume.
How do they do that? Do they, pull the receptors back inside the cell?
They do that, yes, but they also go deeper, down to the actual DNA. The continuous overstimulation leads to the accumulation of a specific transcription factor called delta FosB inside the nucleus of the cells in the nucleus accumbens.
A transcription factor, meaning it changes how the genes are read.
Yes. And delta FosB is unique because it is exceptionally stable. Most transcription factors degrade quickly, but delta FosB lingers for weeks, even months.
Oh, wow.
It sits on the DNA and alters gene expression over long periods. It actually causes the neuron to grow new physical branches, new dendritic spines. Fundamentally restructures the physical wiring of your brain's reward circuitry to prioritize that specific superstimulus over natural, healthy rewards.
So your baseline gets completely warped.
Yes.
Normal, everyday joy is a walk in the park, a good conversation they stop registering because the physical shape of your neurons has been recalibrated by delta FosB to only respond to massive spikes.
That is the biological definition of addiction. And to understand just how powerful this system is, look at the clinical detail from the StatPearl source regarding Parkinson's patients.
Oh, this part was wild.
Right. We mentioned earlier that in Parkinson's, the A9 dopamine neurons die, trapping the patient in their own rigid body. The standard, miraculous treatment is a drug called LDAP.
LDOPA is a precursor to dopamine, right? Because you can't just swallow a dopamine pill.
Correct. Dopamine cannot cross the blood-brain barrier, but LDAP can. Once inside the brain, enzymes convert it into raw dopamine.
Okay.
For a Parkinson's patient, this is life-changing. It restores the fluid to the transmission, the stiffness vanishes, and they can walk again. But there's a devastating documented side effect called dopamine dysregulation syndrome.
Because the LD-DOPA doesn't just go to the A9 movement pathway.
Exactly. The pill doesn't know where it's supposed to go. It floods the entire brain. This means it also floods the A10 mesolimbic pathway, the reward center.
And what does that do?
In a tragic subset of patients, this accidental overstimulation of the D1 and D2 receptors utterly hijacks their behavior. You have cases of elderly patients who have never gambled a day in their lives, suddenly sneaking out at 2 a.m., driving to casinos, and blowing their life savings on slot machines.
Wait, really? Just from a pill?
Yes. Or developing compulsive shopping habits or extreme hypersexuality.
That is deeply unsettling. I read about one patient in the literature who suddenly started painting obsessively thousands of canvases, unable to stop, all because of an L-duo dose adjustment.
Powerful stuff.
It makes me question everything about agency. I mean, are our personalities, our desires, our willpower just an illusion created by receptor density? If a pill can turn a grandfather into a compulsive gambler, where is the self?
It is a profoundly unsettling question. It doesn't necessarily mean we lack free will, but it forces us to admit that our free will operates strictly within the confines of our biological hardware. When you introduce a pharmacological flood of dopamine, that chemical signal can become so loud that it overrides the prefrontal cortex's ability to exert rational control.
The wanting becomes an irresistible physical force.
Exactly.
And this brings us right back to you listening to this. You might not be taking L-DOPA or cocaine, but you are absolutely interacting with superstimuli. Your reward system is an ancient, meticulously balanced machine. It evolved to motivate you to hunt for scarce berries, to build a fire, to seek out a mate.
Yeah, it was designed to handle a trickle of dopamine earned through immense physical and cognitive friction.
But today, you are feeding that exact same delicate receptor system with highly engineered, frictionless superstimuli.
We are overfed on cheap dopamine, but starving for genuine purpose. The system is overwhelmed, the delta phos B is accumulating, and the everyday rewards of life feel completely empty.
Okay, so the receptors are the engine and the brakes. But what's actually driving the car? Like, how does the brain know when to flood the synapse with dopamine in the first place? It can't just be random.
It is the furthest thing from random. It is a highly calibrated prediction algorithm. This brings us to a concept that completely revolutionized neuroscience in the late 90s, the reward prediction error hypothesis.
This is the work by Reed Montague, Peter Dion, and Terry Sejnowski. They were building computer models of learning, right?
Yes, they're computational neuroscientists trying to teach artificial systems how to learn from their environment. They realized that the algorithms they were writing in computer code perfectly matched the firing patterns of A10 dopamine neurons in living brains.
That's crazy.
It is. According to this theory, dopamine does not fire simply because you received a reward. Dopamine fires when you receive a reward that is unexpected.
I need you to break that down. If I order my favorite pizza and I know exactly how good it tastes and I eat it, no dopamine.
If the reality perfectly matches your expectation, there is absolutely no phasic dopamine spike. The dopamine firing rate stays completely flat at its baseline.
But I still enjoy the pizza.
You enjoy, that's the hedonic liking opioid system we talked about earlier. But the dopamine system, the learning and motivation system, stays quiet.
Why?
Because the system is saying, we already knew this pizza was good. We predicted it perfectly. There is no new information here. There is nothing to learn. Dopamine is fundamentally a teaching signal.
So when does it spike?
It spikes when you get a positive prediction error. Imagine you order that pizza, but the restaurant accidentally includes a free side of incredible garlic knots you weren't expecting.
Oh, I love that.
Right. The moment you realize you got an unexpected bonus, your A10 neurons fire a massive, short-lasting volley of dopamine. The signal tells the rest of the brain, update your models. The world is better than we thought. Remember exactly what we did to get this outcome.
And what happens if the prediction is wrong in the other direction? Like, what if I open the pizza box and they burn it to a crisp?
Then you experience a negative prediction error. In this scenario, the dopamine firing rate actually drops below its normal background baseline.
A little baseline.
Yes. The neurons essentially turn off for a moment. And that sudden dip in dopamine feels physically terrible. It is the raw biological sensation of disappointment. It's a harsh teaching signal saying, downgrade the value of this restaurant. Our prediction was way too optimistic.
That is brilliant. But it raises a massive anatomical question. For the A10 neurons to calculate the difference between the expectation and the reality, some other part of the brain has to be generating the expectation in the first place. Where are these predictions coming from?
For a long time, we thought these predictions were generated solely within the cerebral cortex and the basal ganglia. But the recent research you provided points to a massive paradigm shift. The predictions are heavily reliant on the cerebellum.
The cerebellum, that's the structured, cauliflower-looking thing tucked under the back of the brain, right?
That's the one.
I thought that was strictly for motor control. Like, it's the thing that keeps you from falling over when you walk, or helps a pianist play smoothly.
That was the neuroscience dogma for a century. But the cerebellum is not just a motor controller. It is a massive, universal predictive engine. It contains more than half the neurons in your entire brain, tightly packed into this incredibly uniform crystalline architecture.
Half the neurons.
Yes. And what it does is build what we call internal forward models.
What does that mean, a forward model?
When your brain decides to move your arm, it sends a command down to your muscles. But it also sends a copy of that command, an efference copy, to the cerebellum.
Okay.
The cerebellum takes that copy, combines it with the sensory data coming in from your eyes and skin, and mathematically predicts the future state of your body, milliseconds before the arm actually moves.
It's predicting the future so it can correct errors on the fly. There's a study in the notes that perfectly illustrates this with a wrist tracking task.
Yes. Researchers had subjects sit at a computer and use a joystick to track a moving target on a screen. Healthy control subjects had a tiny reaction delay of about 66 milliseconds.
Which is incredibly fast.
It's so fast because they aren't just reacting. Their cerebellum has built a forward model of the target's trajectory. They're smoothly predicting where it's going to be. But then, the researchers tested patients with cerebellar ataxia, people who have physical damage to their cerebellum.
And their delay was catastrophic, 172 milliseconds.
Over a tenth of a second behind reality. Without the cerebellum generating those internal forward models, their movements were meandering, jerky, and always overcorrecting.
They completely lacked the predictive computation.
Exactly. They were trapped in a constant state of reacting to the past rather than predicting the future.
That makes sense for physical movement, but how does this tie back to dopamine and reward?
Because the paradigm shift is that the cerebellum doesn't just predict physical kinematics, it predicts rewards. Studies mapping the cerebellum show that a specific region called the posterior vermis is heavily activated by drug cues in individuals with substance use disorder.
Wait, so the cerebellum is anticipating the high?
Exactly. It has learned the sequence of events, seeing the drug paraphernalia, the environment, the people, and it builds a forward model predicting the impending dopamine rush. It sends that prediction to the VTA to calculate the prediction error.
And it gets even deeper than that. The sources highlight another area, the cursa second of the cerebellum, which is critical for social mentalizing.
Social mentalizing is your ability to infer the goals, beliefs, and hidden mental states of other people. Human behavior is deeply motivated by social rewards. A smile, a nod of approval, a laugh at your joke.
So the cerebellum is predicting social interactions the same way it predicts a moving target on a screen.
Precisely. It automatizes the chronological sequences of social actions to maximize social rewards. When you are in a conversation, your cerebellum is predicting what the other person is going to say next, how they're going to react to your tone of voice. It allows you to smoothly prepare your next social move. Imagine having that 172 millisecond lag in a social setting.
You'd miss the sarcasm, you'd step on their sentences, the conversation would feel jerky and exhausting.
Exactly. The cerebellum generates the expectation of the social reward, and the dopamine system calculates the error.
I want to try an analogy here to see if I have this right.
Go for it.
The cerebellum is basically your brain's internal predictive text algorithm. When you're typing a text message on your phone and the algorithm guesses the exact boring word you want next, you don't even think about it, you just keep typing. There is zero prediction error, the dopamine stays flat, but when you mistype and the predictive text autocorrects it to something completely wild and hilarious that you didn't expect, you burst out laughing. You get a thrill. You only get the spike when the algorithm's prediction is violated in a positive way.
That is a phenomenal way to conceptualize it. If the brain anticipates an outcome and gets exactly what it anticipated, the learning is complete. The system stays quiet.
And think about what this means for your daily life. This perfectly answers the paradoxical question we started with. Why do you feel empty the more you consume? Look at the modern world. We have engineered our environment to be entirely, flawlessly predictable.
We have. When you open a delivery app, you know exactly what food is coming, what it will taste like, and the GPS tells you exactly the minute it will arrive. When you scroll a social media feed, the algorithms have tailored the content so precisely to your psychological profile that every video is entirely expected.
The reward prediction error drops to absolute zero. You are possessing the reward, you are eating the food, you are watching the video, but there is no unexpected thrill.
None at all.
Your brain is a prediction machine that thrives on the friction of the unknown, the challenge of learning something new, the effort of overcoming an obstacle. When you remove all the friction from life, when everything is instant, frictionless, and guaranteed, you literally starve the dopamine system of the very prediction errors it evolved to process.
You are feeding the system empty calories. The death of meaningful friction in our daily lives is the birth of modern existential dread. If there is nothing to predict, there is nothing to learn, and there is no dopamine release to signal that your actions matter.
That is profound. And it gets even more complex because this predictive, dopamine-driven architecture doesn't just dictate our scrolling habits. It is the very foundation of how we think.
Right, because we are moving from the deep ancient structures of the basal ganglia and the cerebellum up to the very top of the evolutionary cortical hierarchy, the prefrontal cortex or the PFC.
This is the region right behind your forehead.
Yes, it is the seat of executive function, working memory, and what we generally consider high-level human intelligence and cognitive flexibility.
And the PFC operates entirely differently from the older, more primitive parts of the brain, right? The sources contrast it with the amygdala.
Yes, the amygdala is heavily involved in processing fear and basic emotional valence. It operates largely using what neuroscientists call labeled lines.
Labeled lines, like a dedicated phone wire.
Precisely. They are hardwired incredibly loud, unambiguous signals. If you are walking in the woods and you see a snake, a specific dedicated neural circuit in the amygdala fires a massive spike of activity that translates to fear. Run.
No nuance.
Right, it is highly specialized, stereotypic, and inflexible. You want it to be inflexible because pausing to ponder the nuance of the snake could get you killed.
But the prefrontal cortex doesn't have labeled lines. The research paper uses this incredibly poetic phrase. It operates with a hum of whispers.
It's a beautiful description of a concept called mixed selectivity. In the PFC, you don't have one specific neuron dedicated to one specific thought or rule. If you did, you would run out of neurons trying to encode every possible thought in the universe.
That makes sense.
Instead, neurons in the PFC wear multiple hats. A single neuron might fire a little bit when you see the color red, and fire a little bit when you hear a bell, and fire a little bit when you remember a math equation.
So thoughts and memories aren't stored in individual cells. They are distributed across huge networks. They exist in a high-dimensional representational space.
Exactly. It creates an infinitely flexible system, but it introduces a massive problem.
Which is?
If every neuron in the PFC is whispering multiple different things at once, how does the brain keep this from descending into absolute chaos? When you're trying to read a dense report for work, how do you focus on the words without the whispers of what you're having for dinner? Or the whisper of a song stuck in your head completely drowning it out?
Right. How do you tune the radio to one station when the dial is picking up 100 broadcasts at once?
The brain uses two main gatekeepers to organize this high-dimensional space. The first is oscillations. These are electric fields, rhythmic fluctuations in the electrical activity of millions of neurons, brainwaves. They act like an orchestra conductor, temporarily forcing groups of neurons to fire at the exact same frequency so they can share information cleanly.
And the second gatekeeper is neuromodulation, specifically our old friend dopamine.
Dopamine sets the state of the entire prefrontal network. It decides whether the network needs to be rigid and stubbornly focused on one task, or loose and flexible to incorporate new information.
Okay, this brings us to the flipped dual state theory from the sources, and I really need your help with this because it totally inverted what I thought I knew.
Let's break it down.
I thought the D1 receptors, the gas pedals, were responsible for locking a memory in place, and the D2 receptors, the brakes, destabilized it.
That was the classical neuroscience dogma for a long time, largely based on spatial working memory tasks in animals. It made intuitive sense. D1 turns on the KMP factory, giving the cell the energy to hold the memory stable. D2 turns off the factory, letting the memory decay so you can think about something else.
But the recent research looking at abstract, action-independent decision-making found that this dynamic is entirely reversed. It's flipped.
It is a remarkable finding. When you are dealing with complex, abstract thoughts, not just remembering where a piece of food is, but weighing different conceptual strategies activating the D1 receptor actually shifts the network into a flexible, dynamic coding regime. It opens the gates.
Oh, wow.
It allows the neural representation to morph and change dynamically over time.
Why would you want the representation to morph? Doesn't that mean you're forgetting the thought?
No, it means you are making the thought robust against distractions. Think of it like holding an idea in your head while walking through a noisy crowd. If your neural representation is perfectly rigid, the first distraction that bumps into you shatters it.
Oh, I see.
But if the D1 receptors allow the network to be dynamic and flexible, the thought can weave around the distractions and sustain itself.
So D1 is the flexibility, and D2 is the stability. D2 locks in a stable, persistent coding regime to execute a computed decision. I was trying to come up with an analogy earlier. I don't like calling dopamine a traffic cop. It feels too passive. What if D1 is the clutch in a manual car and D2 is the gear shift?
I like where you were going with this. Expand on it.
When you push the clutch in, when D1 activates, you disconnect the engine from the wheels. The engine, your mind, can rev freely. You can effortlessly move the stick shift around, considering all these whispering options, changing your strategy. You are highly flexible, but you aren't moving forward.
Right.
To actually execute a decision, you need D2. D2 stomps on the gas, lets the clutch out, and drops it into gear. It locks you into a stable state so you can drive forward with an action.
That is a phenomenal mechanistic analogy. And the precise balance of clutch and gear shift is mediated by the amount of dopamine hitting the prefrontal cortex.
Think about your own daily focus. When you experience brain fog, when you sit at your desk and feel completely overwhelmed, unable to hold a thought or make a single decision, you are experiencing a breakdown in this delicate neuromodulatory gating.
Your D1 and D2 receptors are struggling to balance cognitive stability with cognitive flexibility. You are bombarding the system with too many inputs. You have audio playing, 3 instant messaging apps open, your phone buzzing on the desk.
You are forcing the clutch in and out 100 times a minute.
Yes. The system is overwhelmed. The hum of whispers turns into a deafening roar of static, and you stall out.
Which perfectly explains why a dopamine fast actually works. It's not about punishing yourself, it's about removing the chaotic inputs to let the D1 and D2 receptors recalibrate. It's about returning to a state where you can intentionally shift gears again.
We have spent this entire discussion marveling at how dopamine drives human behavior. It governs our complex addictions, our cerebellar predictions, our highest levels of prefrontal thought. It feels intrinsically, uniquely human. But I want to pull the lens all the way back now, because the most surprising thing in the research is that this chemical is not human at all.
It's not even animal. Dopamine predates nervous systems entirely.
It is a humbling, staggering realization. Plants synthesize catecholamines. They produce dopamine, epinephrine, and norepinephrine.
When I read the list of plants in the source material, I actually laughed out loud. Dopamine is found in high concentrations in bananas, particularly the keel. It's in avocados, it's in apples, tomatoes, and potatoes.
And they don't just happen to have it. They synthesize it using the exact same initiating biochemical steps that mammals use.
That's wild.
Plants use enzymes like tyrosine hydroxylase and tyrosine decarboxylase to convert the amino acid tyrosine into L-DOPA and then into dopamine. The evolutionary conservation of this pathway is breathtaking.
But why? I mean, a potato does not have a brain. It does not feel pleasure. It does not crave cocaine. It is not trying to focus on a spreadsheet. Why on earth does a potato need a dopamine system?
Because while it doesn't have a nervous system, it still has to survive in a fundamentally hostile environment. In plants, dopamine functions primarily as a highly potent, water-soluble antioxidant.
So it's protecting the plant's cells.
Yes. Its specific molecular structure makes it incredibly effective at scavenging free radicals and suppressing oxygen uptake, protecting the plant's tissues from oxidative stress. It also regulates plant growth by interacting dynamically with plant hormones like auxin.
But the defense mechanisms are the part that blew my mind. The research shows that when a plant is stressed by an environmental threat, its dopamine system kicks into overdrive.
It does. When a plant is attacked by a pathogen, dopamine is rapidly synthesized and recruited to build physical fortifications. Take the example of Phytophthora infestans.
That's the fungus that caused the Irish potato famine, right?
Yes, an incredibly destructive pathogen. When a potato plant senses that it is being invaded by this fungus, it produces compounds called hydroxycinnamoyl tyramine conjugates.
Which are derivatives of the dopamine pathway.
Exactly. And the plant doesn't just flood its system with them, it actively transports these dopamine derivatives and deposits them directly into its cell walls. It uses the dopamine to cross-link the polymers in the wall, making them rigid, tough, and impermeable. It builds a literal physical barrier to trap the fungal infection and stop it from spreading.
The cosmic irony of this is just incredible to me. Think about it. When I get stressed out by my environment, a looming deadline at work, a conflict in a relationship, my overstimulated modern dopamine system makes me want to avoid the friction. It makes me want to compulsively scroll my phone or seek out a cheap, hyper-palatable snack to soothe the stress.
Right.
But when a potato gets stressed by a deadly fungus, its dopamine system builds a literal physical fortress to fight off the invader. The potato is handling its existential dread more productively than I am.
It is amusing,
Yeah.
but it points to a profound, unifying evolutionary truth. In plants, stress from drought, ultraviolet radiation, or physical wounding causes a massive spike in dopamine synthesis. It triggers survival behaviors and structural fortifications.
Interesting.
In early animals, environmental stress triggered dopamine to motivate foraging, hunting, and problem solving. Across all kingdoms of life, dopamine is fundamentally an ancient biological tool for dealing with environmental friction and stress.
Which brings us to the synthesis of everything we've explored today. We have traveled from the dark, pigmented neurons of the substantia nigra up through the predictive 66 millisecond algorithms of the cerebellum. We've navigated the flexible, whispering networks of the prefrontal cortex, and we've ended up staring at the chemical fortress of a stressed potato.
And we return to the paradox. Why do you feel more empty the more you consume? The answer is etched into the very biology we just dismantled. The dopamine system, from the simplest plant to the staggering complexity of your prefrontal cortex, is fundamentally designed to help organisms navigate friction.
Whether that is a plant fighting a fungal infection, an animal seeking scarce food in the frozen wilderness, or a human predicting complex, nuanced social dynamics. Dopamine is the chemical of pursuit. It requires effort, it requires resistance, and it fundamentally requires the unexpected to function properly.
But look at what we have built. We have engineered a modern society obsessed with frictionless living. Instant delivery, frictionless algorithmic feeds, artificial intelligence writing our emails and summarizing our thoughts. We have systematically, methodically removed the physical and cognitive struggle from our daily existence.
And your biology is revolting. Your dopamine system is chronically overstimulated by cheap, predictable rewards, but it is fundamentally underutilized in its true evolutionary purpose. You possess the reward without the pursuit. And neurobiologically, possessing a reward without the friction of the prediction error, without the struggle of the climb, registers in the brain as absolute emptiness.
We are suffering from a neurological famine of meaning. The death of meaningful friction is the root of modern brain fog and existential dread.
So, what is the antidote? The antidote to this digital isolation isn't just to arbitrarily throw your phone in the ocean. It is a radical return to purpose. It is about intentionally, forcefully injecting meaningful friction back into your daily routine. You have to redefine the dopamine fast for the modern era. Trade 1 hour of passive, frictionless consumption for 1 hour of productive struggle.
Learn a complex analog hobby that requires mastery over time. Engage in deep, focused work where the D1 and D2 receptors are forced to balance stability and flexibility. Build a physical community where the social interactions aren't mediated by a predictable algorithm, but are subject to the beautiful, unpredictable lag of real human connection.
Feed your brain's biological hunger for purpose, not just its receptors for cheap stimuli, because the machinery is sitting right there in your head, incredibly powerful and perfectly tuned, just waiting to be used for what it was actually built for.
You just have to give it a mountain to climb.
I want to leave you with one final lingering thought to mull over today as you go back to your life. If your brain evolved over millions of years, specifically to calculate the difference between what you expect and the surprises you actually get, how much of your unhappiness today is simply because your world has become entirely, hopelessly too predictable?
It is the most important question you can ask yourself.
Think about that the next time you reach for your screen, expecting to find water and only coming up with sand. Thank you for joining us on this deep dive.
Imagine for a second that you are just, going about your normal day. You're sitting at your desk, you've got a pair of those sleek wireless earbuds in, and you're just listening to a playlist while you power through some emails.
Right, a totally normal scenario.
Exactly. It feels completely mundane, it feels private, but quietly, imperceptibly, those everyday earbuds are doing, well, so much more than just playing audio. Because the skin inside your ear canal is actually highly conductive, and it sits just millimeters away from major neural pathways.
Yeah, which a lot of people don't realize.
Right. So what if those earbuds are constantly scanning the tiny electrical impulses that are just firing across your nervous system?
It's a wild thought.
We are looking at a scenario where your most private, unspoken thoughts, your hidden fatigue levels, the tiny spikes of cortisol you feel when your boss messages you.
Oh yeah, we all know that feeling.
Yeah, exactly. And your subconscious emotional reactions are all being downloaded, categorized, and just shipped off to a server. You think you are alone in your head, but, well, you're not.
You're really not. And it fundamentally upends our entire understanding of privacy. I mean, the idea that the sanctuary of our own minds, which is, the one place we consider strictly our own, might already be compromised. That isn't science fiction anymore.
No, it's really not.
We are standing on the precipice of this profound technological and, frankly, legal shift. The boundary between our biological autonomy and corporate surveillance it's never been more porous. And the hardware required to bridge that gap, well, it's already sitting on our desks, strapped to our wrists.
Which is exactly why we are here today. We are here to pull apart the mechanics of this shift. We are going to dismantle the illusion that our minds are entirely our own by looking at the hidden ethics of brain-computer interfaces, or BCIs.
Right.
And really, the very real end of mental solitude. That's the mission for this deep dive. We're breaking down how neural implants and everyday wearables translate completely private electrical impulses into legible, highly harvestable data.
And it is highly harvestable, yeah.
Extremely. And to figure all this out, we are drawing on a vast landscape of current research. We've got policy briefs from international think tanks like CSIS, peer-reviewed journals spanning bioethics and neuroscience, like Bioethics Open Research and Neuron.
Some really heavy hitters.
Yeah, absolutely. Plus legal analyses of the proposed Federal Mind Act and some sweeping industry privacy audits that are, frankly, pretty terrifying. So, okay, let's unpack this. How did we get here so fast?
Well, it is a really complex web of neuroscience, law, and mostly corporate ambition. We are moving so rapidly from a world where we only worried about our digital footprint, the conscious actions of what we click, type, and buy.
Right, the stuff we actually choose to do.
Exactly. We're moving from that to a world where we have to manage our cognitive footprint. Proprietary algorithms are reaching a point where they effectively claim ownership over subconscious intent. If we connect this to the bigger picture, the final frontier of human privacy is being actively transformed into a harvestable commodity.
A commodity.
That's
That's such a heavy way to look at it, but it's true.
Yeah.
Let's really get into the mechanics of what is actually being tracked, because the definition of neural data has, expanded massively over the last few years.
Oh, totally.
Historically, that term meant a clinical setting, right? Like an electroencephalogram, an EEG, being run by a neurologist to diagnose epilepsy, or an fMRI mapping blood flow to find a tumor.
Right, medical procedures.
Yeah, and that data is highly regulated. It's locked down under strict medical privacy frameworks. But the technological landscape has, it's totally bypassed the hospital at this point. We are now dealing with what neurobiologists classify as cognitive biometrics.
And that transition right there from the clinic to the consumer market, that is precisely where the vulnerability lies. Because cognitive biometrics encompasses this traditional neural readings, sure, but it expands the umbrella. It includes data collected from consumer Internet of Things devices.
The stuff we use every day.
Exactly. We are talking about virtual reality and extended reality headsets. We are talking about fitness wearables, smartwatches, sleep rings, biometric straps.
Basically half the stuff people get for their birthdays now.
Right. And these consumer devices, they are equipped with incredibly sophisticated biosensors. They track eye movement, heart rate variability, skin conductance, and even surface-level brain waves.
And I think the crucial distinction here is how that peripheral data actually maps back to the brain. Take heart rate variability, or HRV.
That's a great example.
Right, because a smartwatch isn't just counting beats per minute to tell you how many calories you burned on a run.
Yeah.
It is measuring the microscopic millisecond differences between each individual heartbeat.
Yep.
And that variance is directly controlled by the autonomic nervous system.
Yeah.
It's that tug of war between the sympathetic nervous system, the fight-or-flight response, and the parasympathetic nervous system, which is your rest and digest mode.
Exactly.
So when an algorithm analyzes HRV, it is essentially reading the real-time load on your nervous system, right?
It is. The physiological mapping is incredibly precise. When you experience a spike in emotional arousal, and that could be fear, it could be excitement, attraction, whatever, your autonomic nervous system alters that millisecond variance before you even registered the emotion consciously.
Before you even know you're feeling it.
Exactly. You haven't formulated the thought yet, but your body has already reacted. And similarly, when you put on an XR headset, the inward-facing infrared cameras track your pupil dilation and your saccadic eye movement.
Little twitches your eyes make.
Right, those rapid little movements. Pupil dilation is actually directly linked to the locus coeruleus in the brainstem, which is the part that regulates arousal and cognitive load.
Wow.
So these are physical, biological metrics, yes, but they serve as direct, unfiltered proxies for your internal cognitive and emotional states.
Which translates into this new field called biometric psychography.
Yes.
And the whole idea here is that companies aren't just logging raw biological outputs like, oh, your heartbeat this fast. They are feeding those signals into massive machine learning models.
That's where the real magic or danger happens.
Right. The algorithm takes your pupil dilation, cross-references it with the exact visual stimulus you are looking at in, say, a virtual storefront, and it begins deducing highly intimate traits. Like, researchers have actually demonstrated the ability to use this combo of peripheral biometrics to predict things like sexual orientation, to map out personality traits, identify a history of drug use, and even flag underlying mental health conditions.
It's staggering what they can infer.
It really is. They can even uncover sensitive proxies for PI numbers just by monitoring the subconscious neural spikes that happen when a user sees numbers that are familiar to them.
Yeah, that peon number study was a real wake-up call for the industry. The sheer power of the inference is what makes biometric psychography so incredibly potent.
Because the raw data by itself is basically useless, right?
Exactly. The raw physiological signal, the heart rate, the eye movement, the skin conductance, it's essentially meaningless in isolation. It only gains semantic value when the machine learning model applies context. And once it has that context, your body betrays your mind. Which brings us directly to the commercial application of this data. Because once cognitive data gains semantic value, well, it becomes highly lucrative.
Yeah, and a perfect way to visualize this translation from raw data to semantic value is to think about ink on a piece of paper. This is an analogy pulled straight from that neuron paper we were looking at.
It's a really good analogy.
It is, because if you look at the raw physical properties of ink, it has absolutely no intrinsic meaning. It's just chemical pigment arranged in random shapes on wood pulp.
Right.
It only becomes a story or a threat or a confession when a reader, someone who actually understands the underlying language model, processes those shapes.
Yep.
In this scenario, the algorithm is the reader. It translates your physiological squiggles into a deeply personal narrative. And I mean, companies are already utilizing this narrative to optimize their workforces.
They absolutely are.
Take SmartCap Technologies, for example. Over 5,000 companies globally are utilizing these devices right now. They are essentially hard hats or headbands with integrated EEG sensors that continuously monitor workers' brainwaves to track fatigue levels in real time.
And, the surface-level justification for SmartCap and similar neuromonitoring tools is always safety.
Of course, it sounds great on paper.
Right. If an employee is operating heavy machinery or managing a power grid or driving a long-haul truck, detecting microsleeps or dangerous fatigue before an accident occurs is a tangible, undeniable benefit.
Yeah, nobody wants a sleepy truck driver.
Exactly. But the underlying economic incentive is biological optimization. If an employer has the infrastructure to track fatigue, they inherently possess the infrastructure to track focus, engagement, and distraction.
Which means the privacy trade-off is just immense. The right to let your mind wander, the right to internalize a bad day, or simply the right to exist unobserved while you perform manual labor, it's just chipped away.
Completely.
Employees are no longer just evaluated on the physical output of their labor, they are being evaluated on the biological efficiency of their actual cognition.
It's a whole new metric for HR.
It really is. And that optimization extends from the workplace right into consumer retail through micro-targeted advertising. I mean, think about it. If I'm wearing a mixed reality headset and I'm navigating a virtual storefront, the inward-facing sensors know exactly what visual stimulus cause my pupils to dilate.
Down to the millisecond.
Right. So advertisers can identify what my brain desires before I've even formulated the conscious thought to make a purchase.
Which totally changes the game.
Right.
Traditional advertising models, they rely heavily on persuasion.
Right, like a billboard or a TV commercial.
Exactly. They present you with information, they try to evoke an emotion, and then they basically hope your conscious mind decides to act on the stimulus.
Yeah.
But micro-targeted advertising driven by cognitive biometrics, it structurally bypasses the conscious decision-making process.
It skips the middleman.
It does. It exploits pre-behavioral processes by targeting affective and conative states, your raw emotions and deep-seated desires, right at the biological level.
Okay, I'm going to push back on the novelty of this threat for a second, though, because we already exist in a hyper-surveilled advertising ecosystem.
That's true.
Right. I mean, I give up my browsing data to social media algorithms every single day. The algorithm knows my click-through rates, my dwell time on specific images, my purchase history, my entire social graph.
Oh yeah, they know everything.
Right. And it targets me with terrifying accuracy. So how is an advertiser monitoring my pupil dilation biologically actually any more dangerous than the behavioral profiling that's already happening on my phone right now?
That is the big question. And the distinction really lies in the timeline of human agency.
That timeline.
Yeah. Traditional browsing data, no matter how granular it is, tracks what you did. It's a historical record of conscious actions. You chose to click a link. You chose to type a search query.
Even if I didn't want to, I still physically clicked it.
Exactly. You exercised a degree of agency, even if that agency was heavily manipulated by sneaky interface design. Cognitive biometrics, on the other hand, track what you feel before the conscious mind even has a chance to intervene.
Wow. So it bypasses the defensive filter entirely.
It is entirely preconscious. When an algorithm establishes your physiological coastline, it can identify vulnerabilities in real time.
Okay, give me an example of that.
Well, imagine an XR system detects a subtle biometric spike indicating acute anxiety. An advertiser could instantly serve a targeted intervention, perhaps an ad for a calming supplement, or some high-margin impulse purchase, precisely when your biological data confirms your impulse control is at its absolute lowest.
Oh, that is so predatory.
It really is. It stops predicting behavior based on past actions and starts reading and exploiting biological states at the exact moment of maximum susceptibility.
Okay, so if an AI can read our preconscious physiological reactions just to sell us things, that predictive capability is inherently a massive vulnerability. And vulnerabilities don't just attract advertisers, right? They redefine how we interact with our own healthcare, which moves us into this realm of digital phenotyping.
Yes, digital phenotyping is a fascinating and complex area.
And just to define that for everyone, this is the process of using data from smartphone sensors, wearables, and artificial intelligence, specifically things like machine learning and natural language processing, to quantify human behavior and map it onto clinical profiles.
Right. It represents an attempt to extract psychological markers from our daily digital exhaust. And the applications are just highly sophisticated. Consider vocal biomarkers, for example.
Yep.
An AI application doesn't just process the semantic meaning of the words you speak into your phone anymore. It analyzes the actual mechanical production of your voice.
The mechanics of that are so fascinating. There are apps out there, like Kintsugi, that analyze vocal patterns to detect moderate to severe depression. And the way it works is, when a person experiences clinical depression, psychomotor retardation often occurs.
Everything slows down.
Exactly. And this subtly alters the tension in your laryngeal muscles and your vocal folds. It actually changes the microtremors, the cadence, and the formant frequencies of your voice.
Things the human ear can't even pick up.
Exactly. The AI is listening for the physiological signature of neurological distress, completely independent of the actual words you are speaking. You could be saying you're having a great day, and the AI knows you're not.
And natural language processing models take this even further by analyzing syntax and vocabulary choice. In clinical trials, AI has successfully detected linguistic markers, changes in sentence structure, pronoun usage, and semantic coherence that are associated with a schizophrenic episode weeks before the patient actually experiences a clinical relapse.
Weeks before. That's incredible.
It is. We are also seeing the deployment of AI therapy chatbots, like Wyza and Youper, that guide users through cognitive behavioral exercises while continuously monitoring their input for signs of acute crisis.
And this whole predictive capacity relies on what is known as the biometric ripple, right?
Yes, the biometric ripple.
Because a major mental health crisis, it rarely just happens instantaneously out of nowhere.
Right, there are always signs.
There is a gradual cascade of physiological and behavioral shifts, like maybe a disruption in your sleep architecture, a really subtle decrease in your typing speed, or even a narrowing of physical movement tracked by your phone's GPS. You just stop going places.
Exactly. The AI acts as a seismograph. It's detecting these microtremors and predicting the earthquake long before the individual consciously realizes they are spiraling.
Right.
And from a clinical perspective, intervening before a depressive episode fully takes hold, that is a massive breakthrough. But the philosophical cost of that intervention is the erosion of human autonomy.
Right. Because if a machine knows your mental state better than you do and can predict your psychological trajectory with a high statistical probability, it fundamentally challenges the concept of a sovereign self.
It really does. Who is in charge, you or the machine?
Exactly. And the danger just compounds when we consider the fallibility of predictive analytics, because these models, they operate on statistical probabilities, which brings us to a really critical flaw in the whole system, which is the ergodic fallacy.
Ah, yes. The ergodic fallacy is such a crucial concept to understand here. It is essentially the mathematical mistake of applying group-level statistical averages to an individual.
Okay, break that down for us.
So an AI model is trained on millions of data points across massive populations. It learns that, on average, a specific pattern, let's say a sudden drop in GPS mobility, combined with increased screen time and disrupted sleep. It learns that correlates strongly with a depressive episode.
Which makes sense on a macro level.
Right. But humans are not statistical averages. We are highly variable. Imagine an employee who just decides to take a week off to completely disconnect.
A staycation.
Exactly. They stay home, they turn off their phone's location services, they binge watch a series, and they sleep at weird, odd hours.
Sounds like a great weekend.
It does. But the algorithm looks at this individual variance, compares it to the group average, and flags the user for severe depressive withdrawal.
Wow. So the algorithm completely misinterprets intentional isolation as pathology.
Exactly, and this is not the only systemic error. These models inherit all the historical prejudices embedded within their training data.
Oh, right. Because AI is only as good as the data you feed it.
Exactly. If an AI is trained on clinical data sets that reflect historical disparities in how marginalized groups are diagnosed or treated by the psychiatric establishment, the algorithm will just automate and scale those exact biases.
Which is terrifying.
It is. We risk creating a system where minority populations are disproportionately flagged as high risk based on completely flawed inherited data architectures.
And beyond the algorithmic errors, we also just have to look at the physiological toll of simply existing under this constant analytical lens. There's this research out of UTS that analyzes the subconscious burden of constant surveillance.
I've read that. It's fascinating.
Yeah, because even when we rationalize it, like when we tell ourselves, oh, I don't care that my smartwatch is tracking my vitals, or we just forget the sensors are even there, our nervous system still registers the panopticon.
That's the thing. The brain is highly attuned to observation. When it registers chronic surveillance, it actually triggers a low-level, sustained stress response.
It's like you can feel eyes on you.
Right. It alters our behavior, prompting this really subtle self-censorship and a persistent anxiety about our own internal states. We begin to police our biological reactions because we know they're being quantified.
That's so
It
dystopian.
really is. The surveillance apparatus moves from the external environment directly into the nervous system itself.
And if an AI therapy bot or a corporate wellness program can predict and influence a mental breakdown, well, that infrastructure is a weapon just waiting to be wielded.
Without a doubt.
Which brings us to the national security implications of neurotechnology. Because if a corporation can exploit your biology for profit, we must examine how adversaries might weaponize this exact same access.
Right.
The transition from commercial optimization to military application is documented really extensively in reports from the Center for Strategic and International Studies, or the CSIS. They've been analyzing the development of neuroweapons.
And we have to be very clear here. We are objectively observing a technological arms race. The evolution of the battle space now includes the human nervous system.
Yeah, the CSIS reports detail the engineering of directed energy systems. And just to be clear, we are neutrally reporting what's in these documents. We aren't taking a stance on any specific country's military policies.
Absolutely. This is purely an analysis of the emerging technology.
Right, so these directed energy systems are non-kinetic weapons. They utilize acoustic waves or microwave energy to directly interfere with neural processing.
And the biological mechanics of these systems are frankly terrifying. Acoustic weapons can be tuned to the resonance frequencies of the vestibular system in the inner ear.
The part that controls balance.
Exactly. And hitting those frequencies can induce severe vertigo, intense nausea, and complete spatial disorientation. And then you have microwave weapons. These leverage the thermoelastic expansion of tissue in the brain, which is often called the Frey effect.
The Frey effect, right?
Yes. And that can actually induce auditory hallucinations or intense cognitive confusion. These aren't weapons designed to cause traditional kinetic trauma like an explosion. They're designed to scramble the brain's fundamental ability to process information.
That is wild.
The reports also outline the development of highly specialized chemical or biological agents that are engineered to selectively impair specific neural functions.
Here's where it gets really interesting. It represents a fundamental shift in asymmetric warfare.
Right.
Because the objective is no longer solely the destruction of physical infrastructure.
No, not at all.
If an adversary can subtly degrade the decision-making capacity of a submarine commander or a drone operator or even a political leader through neurointerference, they achieve a massive strategic victory without ever crossing the threshold of traditional armed conflict.
It bypasses the physical armor completely and targets the biological hard drive. The human operator is the vulnerability.
The ultimate zero-day exploit.
Exactly. And while military applications represent, the extreme end of the spectrum, the underlying technology, the actual hardware required to read and transmit neural data is already proliferating in the consumer market.
Which forces us to look at the regulatory landscape governing the devices we can literally go out and buy today. And the reality is, it's a massive legal void, which is commonly referred to as the I-Pay gap.
Yes. the iPay gap.
Hmm.
It highlights a profound structural failure in how we define medical privacy.
Right.
In the United States, the Health Insurance Portability and Accountability Act provides really strict protections for clinical data. If a doctor orders a neurological scan, that data is securely stored, it's heavily regulated, you have rights over it.
Because it's at a hospital.
Right. But iPay's jurisdiction is strictly limited to covered entities within the traditional healthcare system.
So if an individual purchases a biometric sleep ring or, a consumer EEG headband for meditation at home, that data, despite being medical-grade insight into their central nervous system, falls entirely outside of federal health privacy protections.
It's treated like a toy, legally speaking.
Exactly. Because it is marketed as a consumer wellness device or an entertainment peripheral, it is legally treated no differently than the data generated by a smart toaster.
And this regulatory void has created an environment of rampant exploitation. The Neuroscience Foundation recently conducted this incredibly comprehensive audit of the privacy policies of 30 major consumer neurotech companies.
And the numbers are shocking.
They really are. The data reveals a systemic prioritization of data harvesting over user security. They found that 96.7% of the audited neurotech companies explicitly reserve the right to transfer or sell users' brain data to the third parties.
Wait, 96.7%.
Almost all of them.
That's not an oversight in the legal drafting. That is the core business model.
Absolutely.
Data brokering is the primary revenue stream for many of these platforms. The hardware is just the collection mechanism. And the security standards protecting this harvested data are shockingly low.
Oh, they're practically non-existent.
Right. According to the audit, fewer than 20% of these companies even mention using encryption to secure the neural data they store. And only 16.7% commit to breach notification.
That's the craziest part to me.
Right. Meaning if a server holding your cognitive biometrics is hacked and compromised, the vast majority of these companies are under no legal obligation to even inform you.
None.
Overall, only 10% of the industry met the Foundation's baseline safety measures.
And we have to remember the economic projections for this sector estimate the neurotechnology market will surpass $38 billion by 2032.
$38 billion.
Yes. We are scaling a multi-billion-dollar industry on a foundation of completely unregulated biological extraction. And the critical danger here, the thing people really need to understand, is data permanence.
Yes, because you cannot rotate a cognitive footprint. If a financial database is breached, you call the bank, you cancel the credit card, and they issue a new number.
Simple.
If a password manager is compromised, you reset your credentials. But your neural patterns, your autonomic responses to stress, your baseline physiological signatures, these are biologically hardwired.
You can't change your brain waves.
Exactly. Once your cognitive biometrics are exposed in a data breach, they are exposed in perpetuity. The long-term implications for behavioral profiling, deepfake generation, or identity theft are just unprecedented because the security key is your literal physical biology.
This raises an important question, though. How can society trust these technologies when the default corporate behavior treats the human mind as an open-source data mine?
Well, they shouldn't.
Right. And this realization has triggered a global legal response. Lawmakers are actively, right now, debating how to build a regulatory framework capable of protecting mental privacy. This has sparked the global movement for neurorights.
Neurorights. Okay, let's break that down. The Neurorights framework is built on 4 core pillars. First, you have the right to mental privacy, the absolute control over who can access your neural data.
Crucial.
Second, cognitive liberty, which is the right to self-determination over your own brain chemistry and thought processes. Third, mental integrity protection against unauthorized manipulation or interference with your neural function. And fourth, fair access to cognitive enhancements, ensuring that neurotechnology doesn't create a biologically stratified society where only the rich get better brains.
Right, but implementing these philosophical concepts into enforceable law requires massive structural shift.
Yeah, you can't just wave a wand.
Exactly. Now, Chile has been a pioneering force in this arena. They were actually the first nation to successfully pass a constitutional amendment explicitly recognizing rights tied to brain activity and mental integrity.
They changed their constitution.
Yes, elevating neural data to the absolute highest level of legal protection.
And we've actually already seen how that constitutional amendment functions in practice. Just look at the timeline of the Emotive case. Emotive is a neuroinformatics company that produces these consumer EEG headsets.
Right.
A former Chilean senator purchased one of these devices, used it, and the company's software uploaded and retained his neural data on their cloud servers.
Which was standard practice for them.
Standard practice. But under the new constitutional framework, the senator challenged the company's right to hold that data. And the Chilean Supreme Court ruled against Emotive.
A landmark decision.
Huge. They ordered the company to immediately delete the neural data and severely restricted how they could process user information within the country. It demonstrated that neural rights can be weaponized defensively by citizens to force corporate compliance.
And other jurisdictions are taking different regulatory paths. The European Union, for example, is leveraging its existing data protection architecture.
The GDPR.
Exactly. Under the GDPR, neurodata is increasingly classified as special category data, which requires explicit informed consent for any processing. Additionally, the newly implemented EU AI Act categorizes emotion recognition technology, which, as we've discussed, relies heavily on cognitive biometrics. They categorize it as high risk.
I mean what?
Meaning it imposes strict transparency, testing, and auditing requirements before such systems can be deployed to the public.
Okay, so that's Europe. But in the United States, with the federal HIPAA gap still wide open, state legislatures are having to move to patch the holes themselves.
It's a bit of a patchwork right now.
Very much so. Colorado recently passed legislation redefining biological data to explicitly include neural data, integrating it into their broader State Privacy Act. Montana amended its Genetic Information Privacy Act to encompass neurotechnology.
California is doing something similar with the CCTA updates.
Right. And at the federal level, you have the proposed MIND Act, that's the Management of Individuals' Neural Data Act, sponsored by Schumer, Cantwell, and Markey. And it aims to empower the Federal Trade Commission, the FTC, to step in where the FDA's medical jurisdiction ends. It would grant the FTC authority to restrict the commercial sale and misuse of sensitive neural data.
But the debate over the best legal mechanism is far from settled. I mean, while Chile chose to invent entirely new human rights, legal scholars often point to the approach emerging from Brazil as a highly pragmatic alternative.
Yeah, this is a really interesting contrast.
Because inventing a new right to cognitive liberty is philosophically noble, but legally it's very muddy.
How so?
Well, for instance, if a citizen has a fundamental right to cognitive liberty, does a highly persuasive political advertisement violate that right?
Well, that's tricky.
Right. Does a targeted social media algorithm constitute a breach of mental integrity? Defining the actual boundary of the mind in a courtroom is incredibly difficult.
Right, because where does persuasion end and manipulation begin? So the Brazilian alternative bypasses the philosophical debate entirely. Instead of trying to legally define the mind or invent new constitutional rights, Brazilian lawmakers are utilizing their existing data protection framework, the LGPD.
Yes.
And they apply a legal doctrine known as the pro homini principle.
And the pro homini principle basically dictates that when interpreting the law, the state must apply the standard that offers the greatest possible protection to the human person.
Okay.
So by applying this principle, Brazil can classify neural data as the absolute most sensitive tier of personal data under existing law. They don't need a new constitutional amendment.
That's so smart.
It is. They simply use the existing mechanisms of strict purpose limitation, mandatory data minimization, and heavily regulated consent structures to restrict corporate processing. It regulates the data itself rather than trying to define the thought.
It's a fascinating legal divergence. Like, do we invent sweeping new human rights that might be nearly impossible to enforce, or do we tightly lock down the data itself, treating it like a hazardous material that corporations must have strict clearance to handle?
That's the debate we're having globally right now.
But, while the legal community debates the architecture of tomorrow's privacy laws, the hardware is already on store shelves today.
People are buying it right now.
Exactly. So we need to look at actionable steps for the consumer. How do you protect your mental privacy right now? If someone is listening to this and thinking, well, I want a sleep ring, what do they do?
Establishing a baseline of protection requires understanding the technical architecture of the devices you purchase. You have to read the specs. Industry guidance, like the frameworks from TrustArc, points to 3 critical factors when evaluating consumer neurotech.
Okay, what's the first one?
So first is data minimization and edge processing. Data minimization simply means the sensor should only collect the specific physiological metric required for the immediate task and absolutely nothing more.
Right, it shouldn't be hoarding data just in case.
Exactly. And edge processing is where the real security lies.
I love this analogy. Think of it like cooking a meal.
Yes, go ahead.
Edge processing is like cooking that meal in your own kitchen with the blinds drawn. The ingredients, your data never leave the house. The device processes the algorithm locally on its own internal chip, gives you the result on your screen, and then deletes the raw biological input.
Right.
The alternative, which most companies do, is shipping all your raw ingredients to a massive corporate cafeteria to be prepared under constant surveillance. The moment a continuous stream of your raw, unfiltered brainwaves or cardiovascular data leaves your device and is transmitted to a cloud server, your exposure risk multiplies exponentially.
It's the difference between local and cloud computing, and for biology, local is mandatory. The second technical requirement is robust encryption. And it is not enough for the data to be encrypted just in transit, like while it's traveling over Wi-Fi. It must be encrypted at rest on the device itself. Crucially, this involves secure key management.
Meaning who holds the key to unlock the data.
Exactly. The decryption keys should reside locally with the user. That means the corporation cannot arbitrarily access or monetize the raw biological data, even if they possess the encrypted files on their servers. They just see gibberish.
And the third factor is the consent architecture. Consumers must look for explicit opt-in consent models, not those pre-checked boxes buried deep within a 50-page terms of service agreement that nobody reads.
Right, true opt-in.
Consent must be granular and easily revocable. You should be able to turn it off today. Furthermore, the company must provide a transparent, verifiable data deletion policy.
This is a big one.
Yeah, hitting delete on a user dashboard shouldn't just, hide the metrics from your app screen. It must trigger a cryptographic wipe of the data from the company's back-end infrastructure. They shouldn't still have it.
And these technical standards form the foundation of what we call neurosecurity. The central tenet of neurosecurity is that the protection of biological data must be implemented by design and by default.
Not an add-on.
Exactly. It cannot be an afterthought. It shouldn't be a premium subscription feature or a setting hidden in some developer menu. If a hardware manufacturer is treating cognitive biometrics with the same lax security protocols as a basic social media application, they are exhibiting gross negligence.
Wow. We've really covered the complete life cycle of this technological shift today. We started by looking at the biosensors embedded in everyday wearables, mapping how heart rate variability and pupil dilation serve as these direct conduits to the autonomic nervous system.
It all starts with the sensors.
Right, and then we examined how algorithms translate that raw physiological data into semantic value, basically turning our subconscious reactions into biometric psychography. And that's used to optimize workers and completely bypass the conscious filters of consumers.
We explored the predictive capabilities of digital phenotyping too, analyzing how AI parses the microtremors in our voices to forecast mental health crises, and the inherent dangers of algorithmic bias and the ergodic fallacy.
Right, the danger of treating individuals like statistical averages. We also observed the national security reality of directed energy systems targeting human cognition. And we dissected the systemic privacy failures of a consumer market where, honestly, data brokering is just the default.
But we also see the legal pushback.
Yeah, the enforcement of neural rights in Chile, the regulatory frameworks of Europe and Brazil, and the technical standards required for genuine neurosecurity. So what does this all mean?
It means we are at a turning point.
We are. The collapse of mental solitude is not some far-off future possibility. It is a current mechanical reality. Our most intimate biological signals are highly valuable assets. They are constantly mapped by predictive models and vulnerable to both commercial extraction and adversarial interference. The final frontier of privacy is no longer the walls of your home. It is the physical biology of your nervous system.
The architecture of the mind is now inextricably linked to the architecture of the network. There's no going back.
There isn't. And I want to leave you with a lingering thought to consider. We discussed how AI, through constant physiological monitoring, is becoming capable of detecting our emotional needs, our fatigue levels, and our acute stress before we consciously register those states ourselves. If this technology becomes entirely ubiquitous, if your wearable ecosystem continuously alerts you to what you're feeling before you actually feel it, will we gradually begin to outsource our own self-awareness?
That is the ultimate fear. If the algorithm dictates your internal state, the nature of human agency is fundamentally altered.
Exactly. When the machine tells you who you are you experiencing your own life, or are you simply experiencing the algorithm's interpretation of your biology? Thank you for joining us on this deep dive into the source material. Stay curious, scrutinize the hardware you wear, and guard your cognitive liberty.